smoky. Fellow tranny techs, welcome and thanks for joining us for our little mini clinic today. We want to talk about the ShoreCool technology, but before we do, I have my 2 email addresses and phone number right here. You might want to stop the video and make a note of those things. The disadvantage we have with this type of format is I can't get the feedback from you, but if you have something you think is really important that you want to share, feel free to email me. If you have something that's what you would consider urgent, you need immediate help, and you email it, make sure you text me a message to my cell and say, hey Dean, please check your email because I have something I'd like you to look at. And that way I'll stop and I'll look at it right away. There are times when we may go a couple of days without looking at our email because we're preoccupied with other projects, and we certainly want to give you immediate attention when you need it. We appreciate you guys, we appreciate your support, and we're here to help you. We're going to show this thing in 5 little sniglets. We're gonna break it up into the following chapters. And this way we can break it into smaller portions and videos for posting it online and such. All right, the first thing we want to look at is the OE thermal bypass purpose and function. The question is, what is this all about? Why the big push for thermal systems? Is it really all that necessary? What do they have in mind? So here's the idea. Clutch circuit leakage and shift field change as ATF gets hotter and thinner. You all know historically that leaks get worse when it gets really hot. When the fluid gets thin, you pick up flares, neutrals, things like that. We all know about that. But if the temp and viscosity are maintained within an ideal range, the computer's adaptive strategy can keep shift quality at an optimum with consistency. At least that's the idea. Bypassing the cooler provides a faster warm-up cycle, getting the trans to optimum temperature more quickly, which is maintained by the thermal element, and the story goes on from there. So, what I want to show you now is there are 3 operational states of these thermal bypass systems. We're going to start with the full bypass. I want to thank ATRA for their work in their seminar book. This is actually from the 2011 seminar book in which they explain how the thermal element functions. This is on the 5R55 or 4R55E transmission. You know that one's in the valve body. Here we have a picture of the thermal element and valve, and notice the converter charge goes up through the converter, comes back, and here it's directed either to the cooler on this side, or it's also connected over here to the thermal bypass circuit. Now in this position, this valve in this position, converter out is able to bypass the converter circuit. Now in this slide you'll see that the thermal element has heated up and the little steel pin is expanding and it pushes the valve in the downward position. It blocks the flow from converter out to go around the cooler circuit. This way flow is forced down through the normal channel, through the cooler. Flow coming out of the converter is able to go over here and go through the bypass circuit and directly to lube. Notice you have front, center, and rear lube. Bypassing the cooler. Now that's fine to get the oil warmed up. Alright, in here we see fluid returning from the converter, goes back through the PR valve and up through the drain back valve and enters the cooler supply circuit. Now notice this way it goes through the sections of the pump, loops out, and goes to the cooler there. But there's also a circuit here that bypasses and goes through the flow control valve. There it would go directly down here to the lube circuit, bypassing the cooler. Now imagine, if you will, driving conditions. We're running about 3 gallons per minute from the converter out toward the cooler. But the converter supply, the 3 gallons per minute, is the same as what's coming back here. You know, what goes out comes in. But if it's trying to maintain a temperature, it's feasible that you could be driving along and running a gallon per minute through the bypass circuit and only 2 gallons per minute through the cooler. So 1/3 of the oil could be bypassing. Now the actual amount that bypasses is determined by a lot of variables, but the idea is you see that by regulating the amount of bypass oil, it can maintain a desired constant temperature. Okay, now in the 2 pictures we looked at previously, it showed 2 states. The first was full bypass, when all of the fluid intended for the cooler goes around and directly to lube, bypasses the cooler. The second page showed full cooler flow. Now the first happens when the transmission fluid temperature is below the threshold of the thermal element. Now if the intended average operating temperature is, let's say, 215 to 220 degrees, if the transmission temperature is 235 to 240, then the thermal element will allow full cooler flow. But those are not the default state. The average default state is one in which flow is regulated by the thermal element. The purpose is to try and maintain a constant transmission fluid temperature. And there's a lot of variables in this equation. You have altitude, the ambient temperature, the amount of airflow through the radiator, the efficiency of the cooler, what throttle opening is it? Is under a hard pull? How much converter flow is actually going through the converter? Because it changes as you accelerate or put a hard load under it. So there's a lot of variables, and this thermal element has to adapt continually. It's continually adjusting to training temperature. It's a dynamic system. Now I'm going to show you a circuit from the 5R110 because that's much easier to follow the logistics. It's visually more appealing, so we're going to move this over here. So let's imagine you're driving in a westerly direction on I-10 or 40. Let's say you're heading towards Flagstaff, Arizona, and you've got to climb from maybe 100 or 200 feet above sea level up to about 7,000 feet above sea level. Now, here's what happens during the operational phase. There's going to be times when you're going to be able to do an uphill long run on a slow grade with lockup on. So you'll maintain a steady temperature, but what if you go on a steep grade, step into the pedal, and it releases lockup? Now the torque converter is working harder, it's generating more heat. So the tendency is the transmission fluid temperature is going to rise. So what's going to happen? The thermal element is going to expand. It's going to open up the cooler flow, to actually cause the cooler to flow more oil to bring the temperature down. But now when you get to the top of the hill, now you're in Flagstaff and level out, the load factor kind of evens out. You're driving through the town, and let's say you're 15 degrees cooler temperature than you were when you were down in the desert. All right, so now the airflow and the temperature, the ambient temperature has changed, and so the actual flow requirements through the radiator are different. So now you may have where it does a partial bypass. But now we're going to leave Flagstaff. Let's say we're heading to Yuma, okay, and we're going to have a couple 100-mile downhill run. There's going to be a lot of sections where you're going to be going downhill almost in a coast condition. And what happens? You're at 75, 80 mile an hour, a lot of good airflow through the radiator. You're up on a higher altitude where the air is cooler, and it's going to tend to overcool the fluid. What happens? The thermal element wants to heat the fluid up again. So what does it do? It starts to shut off cooler flow. Well, now if you have a 5 or 55W, now you have a problem because front loop is derived from cooler flow. And now imagine yourself in a Ford Explorer doing a couple 100 miles downhill in a coast condition with no cooler flow, and the overdrive is running in reduction. What are you going to do with all that heat? The planet doesn't get cooled down. So you can see that as you climb up a hill, it increases the cooler flow to bring the temperature down. At a level condition, it may maintain a partial bypass, but then on the downhill, under low load, cooler temperature, not as much heat, it's going to want to bypass the flow again to maintain that higher temperature. So there's a dynamic that's always at work. The problem is when we think of things as either simply on or off, we miss some of the dynamics of how the system works. The other problem is if you have a cold start in a trans like that, you fire the thing up, run down the road, get on the freeway right away. It's doing the warm-up cycle so the cooler flow is bypassed. The problem is overdrive lube comes from cooler return. So now you're running out on the freeway, you're running late for work, and you're doing 75, 80 mile an hour in traffic, trying to get to work, and you have no overdrive lube, or minimal overdrive lube, whatever can leak back from center lube. Now you have another problem. One was a coast condition where it shuts off. This is a cold condition that hasn't warmed up sufficiently as if you had to flow oil to the overdrive. Now, you can guess what happens. Any oil in the overdrive that's there is going to vaporize. That's part of the blackness that you see, the burnt fluid. All right, so now let's look at some of the drawbacks with this system. I've already hinted at one of them. The average operating temperatures in our estimation are too hot. Valve bodies tend to overswell, get valve sticking. Solenoids and solenoid bodies run also very hot, don't work as well. We've proven this. Behavior is less consistent and suffers intermediate issues, or intermittent issues. There are also other dangerous side effects, which I already mentioned, a 55W going downhill for a long ways from a higher altitude. You just shut down the lube to the overdrive planet. Now, stop and think about this a second. When you look at a 55W planet that's burned out and you see the thing is black as the ace of spades, ask yourself, how hot does that planet have to get to turn black? Heat-treated steel? It's pretty high. You'd expect 500 or 600 degrees sustained temperatures in order to do that, or more. That's severe running without cooler flow, or without lube coming from the cooler return. As for the other problems, valve body overswelling, I know Jimmy and I sat and went through a lot of the troubleshooting things on TRNW and other places, and we saw case after case where guys were saying, I had this problem, I had that problem. Solution, replace the valve body. Why? Because they pull the valve body out of the car and they're picking all the valves. They don't find anything stuck. Why? Because the valve body's at room temperature. When it was in the car and it was 240 degrees, the valve body would swell and the valve could stick. But when they drop the valve body at room temperature, it's not stuck anymore. So now the poor fellows are chasing ghosts. We've proved historically that much of the 55W issues, the intermittent problems, were due to a sticking solenoid regulator valve. That's why if you buy the 55W kit, it has a new reg valve in there. There's a stick-resistant design. Because that's what happens. These valve bodies overswell. Now imagine, if you will, you're running out there from a dead stop, dead cold, you're running out on the freeway. Now the overdrive planet is running, and it's getting hotter and hotter and hotter. And you have heat radiated down over the top of the valve body. But the thermal element hasn't received that heat yet. So now you have valve bodies swell in excess before the cooler flow starts. See, this is a functional problem in our estimation. And one last problem I may mention is related to contamination in conjunction with these high sustained operating temperatures. We've seen the little thermal element, the pintle, sticking because of the combination of the two. And of course that throws the whole function out the window. It's not going to be consistent. And what do you do if the system ruptures? Now we're going to take a look at the ShoreCool system. All right, so with most of the blow-off systems, which is found in the 5R110, it's in the pump. With the 5R55W, the thermal element is in the valve body, so our pressure relief is direct to lube in the valve body. In the case of the 6R60, 6R80, the thermal element is in the case above the valve body. So it's inside the trans, but that one is a pressure differential system. All the ones that are in the cooler line blocks, like this, are a pressure differential system. It's basically two styles. Most of the internals, except for the 6R60, is pressure relief. Most of the ones in the cooler blocks are pressure differential. All right, first of all, let's talk about the ShoreCool systems. There are basically two types of thermal bypass. The first type acts like a pressure relief or a blow-off valve. We looked at the 5R110. That's a blow-off valve style, similar to a mainline pressure relief valve. The 5R55W is also a blow-off style. But then we have the ones where they're in a cooler block, like this. Most of you have probably seen that. Okay? And thank you, Jimmy Brookshire, made a beautiful cutaway of a cooler block here. This one you'll see the new STL020 is an internal system. Now this style is a pressure differential. We have cooler lines in and cooler lines out. Coming from the trans to the cooler, goes through here, and when cooler flow is on, goes this way. Return comes in and goes to the tranny here. So on top of this you have converter out, or to the cooler pressure. On the return side, underneath, you have cooler return pressure. Now, since the cooler itself is a resistor, then you're going to have a pressure differential. If you put pressure gauges and flow gauges on cooler lines, you'll see that typically at idle on most trannies you may have, say, 30 psi. But on the return line you could have 5 or 10 psi. So that might represent a 20 psi differential in the pressures. When we were doing the Honda development, we saw 30 psi consistently on the to the cooler at low RPM, and on the return line we'd have 5 or 6. So there was a 25 psi differential. Now, here's what you need to know. When the pressure differential, first of all, in the OE system with the thermal element, the pressure differential is inconsequential because it's either regulating bypass and it's related to flow. But when we have our ShoreCool system, we have it built so that if the difference in pressure between to the cooler and cooler return is greater than 45 psi, it'll blow the ball off inside that seat right in there. And so what it'll do is, if the cooler gets extremely restricted, then that ball will blow open and allow bypass. So basically, if the, let's say that the cooler gets completely blocked, and to the cooler pressure will rise to equal line pressure. So if it's completely blocked, you'll have 65 psi in the out to cooler side, but you'll have 0 on the return side. So what will happen is the bypass system will blow open and it'll bring the pressure up here until it's about 20 psi, because the 45 psi differential plus 20 is equal to 65 on the top side. So at 20 psi you can run 1.5 to 2 gallons per minute. So that means you're going to have consistent flow to the planetaries to keep it from crashing. But it's a pressure differential system. So you have two types. One is a blow-off or pressure relief, and the other is a pressure differential. Okay, so now let's talk about the ShoreCool function. Remember, with the factory system you had 3 operational states. Default was cooler bypassed. The extreme hot state was full cooler flow, but the average operational state, the one that they're most interested in, is the one where it maintains a fixed, predetermined temperature, typically 215 to 225, but sometimes higher. Now, with the ShoreCool system, we have a default state that's full on. In other words, if you put the ShoreCool system in the vehicle, you start the vehicle up. As soon as you crank the engine, fire up, the line pressure starts pumping converter oil right away. You're going to have cooler flow right away. It's default cooler flow on. Now, in an emergency situation where cooler got blocked, now you'll have full bypass. Full lube will bypass the cooler. If it's blocked, it's going to the planetary. With the factory system, if the system got blocked, you're going to end up either severely overheating the oil, or in some states, if the thermal thing is stuck closed, well, you're going to have no oil to the planetary at all. You're going to crash the planets. But in this system here, the normal operational state is with cooler flow turned full on. Now, In an emergency, when a cooler gets blocked, it will have full bypass. But it also has a partial bypass function, and this is the way that will work. When you increase engine RPM, you accelerate, it increases the amount of converter charge and cooler flow, and cooler pressure does rise. So I can imagine a situation where you're going down the road and you have reasonable cooler flow at under 70 psi or so. But now if you nail the pedal and you have high converter flow, 3.5 gallons per minute or whatever coming out of the converter heading for the cooler, cooler pressure can rise, and our system is set so that in the blow-off types, if cooler pressure gets above 70 psi, it will bypass to cooler return. That keeps the cooler pressure from being overpressure, and so when you're in a state like that, it's going to have a partial bypass just to keep the pressure at what we believe is an acceptable PSI. In the older transmissions, Turbo 400s, you can put the thing in reverse and nail the pedal to the floor, and you can have cooler pressure go up pretty high. Most of the older cooler designs could stand up to line pressure, normal mid-throttle line pressure in the radiator, but the newer ones have different construction and different materials. They cannot stand the high pressures. The proof of that is the RE5. When they eliminated the thermal or the cooler bypass valve on that and run line into the cooler, now we're breaking coolers like crazy, and you know that whole story. So with the system here, default to cooler flow on, it'll have high RPM, high load, partial bypass. Now let's talk about cold temperature. We've had guys ask us, well, what about if we're putting the ShoreCool in the thing? And now we're up here in Wisconsin, and we get up in the morning, and now it's 17 below, and we're heading to work at 5:36 a.m. The sun's barely up. The oil is cold and thick. Well, here's the thing. Again, the cooler lines and the cooler itself are a resistor. And with the higher viscosity and ultra cold temperatures, the resistance is increased. So what will happen is, if the oil's that cold and the guy jumps in the car, throws it in drive, and takes off, you're going to have partial bypass that's viscosity driven, not thermally temperature driven like in the thermal element, but our system is a viscosity driven system, which means that you can do hard throttle acceleration in really cold temperature, and you'll bypass right here, which allows it to help preheat the oil until the engine gets up to temperature and the radiator is warmed and the trainee fluid through the radiator can start flowing at a reasonable. So you'll have partial flow through the radiator, but you may have heavy bypass flow because of the extreme cold temperature and the high viscosity. So this system is also dynamic, but what you need to recognize is that it's mechanically dynamic. It's not thermally dynamic by a silicon pack.